All right. Hi, everyone, and welcome to the fifth webinar of the Soil Health Training Program, Organic Matter and Composts. Today's Tuesday, January 16th, 2024. Wanted to start again today by thanking the Lake Champlain Basin Program and NUIPIC for the funding to create and host this Soil Health Training Program. Couldn't have done it without you. Our agenda for today, we'll do a course overview and a homework review. And then we will have Heather Darby here presenting on organic matter and compost with some Q&A interspersed, and then we'll talk about our next class. Again, just to frame where we are, we have officially started part 2 of this training program. And so part 1 was what is soil health and how do we know if soils are healthy? And so now we're officially into how do we manage for soil health, which I think will be a really fun, exciting set of webinars. Quick homework review. Hopefully folks had a chance to read chapter 9 of our textbook, Managing for High Quality Soils and Focusing on Organic Matter Management. There was a lot to learn about, and I'm excited to have Heather kind of speak to some of this stuff and some other things that are relevant on Vermont fields. With that, I'm going to introduce Heather Darby. Heather Darby is an agronomic and soils specialist for the University of Vermont Extension. She received her MS from University of Wisconsin in agronomy and her PhD in crops and soils at Oregon State University. Being raised on a dairy farm in northwestern Vermont has also allowed her to play an active role in all aspects of dairy farming, as well as gain knowledge of the land and create an awareness of the hard work and dedication required to operate a farm. These practical experiences, complemented by her education, have focused her attention towards sustainable agriculture and promotion of environmental stewardship of the land. Heather is involved with implementing many research and outreach programs in the areas of fuel, forage, and grain production systems in New England. Outreach programs have focused on delivering on-farm education in the areas of soil health, nutrient management, organic grain and forage production, and oilseed production. And research has focused on traditional and niche crop variety trials, weed management strategies, and cropping systems development. With that, to Heather, I just realized I didn't make you a host, so let me do that.
Oh, great. It says I can share my screen.
Oh, perfect.
No.
And you can take it away.
All right. Well, thank you. And thanks for inviting me to present at the class. It's been really enjoyable to listen to the webinars that I've been able to make, but also to be a part of kind of organizing the class and sessions and really digging into soil and soil health. And I'm glad everybody's had the chance to participate. I think it's been very valuable to me and hopefully to everybody else as well. Lauren and others had asked if I could talk about soil organic matter, and it said and compost. And I asked Lauren, am I talking about how to make compost? And she said, no, definitely not. And I actually now realize I'm not even, I do talk about compost a little bit, but we can get into compost later if we want. It is definitely a type of soil organic matter amendment that many people use on their farms. And I hope that we can have a really good discussion about building soil organic matter, once we get through some of the, more in-depth, I guess, pieces around what soil organic matter is. And I put demystifying soil organic matter. I probably should have used the same title you had, Lauren, but organic matter is surprisingly complicated. And I feel like my life was a lot easier before I knew all that much about organic matter. And when I first looked at a soil test and it said organic matter, I liked that. That was simple. But the more you get to know about it, the more complicated it becomes, but it also helps sort of inform management and, practices and strategies you can use in your work with farmers or as a farmer to really gain the benefits of what organic matter has to offer us, as well as the environment. All right, so let's start with some of the basics. Soil, Soil is composed of minerals, air, water, and organic matter. And you can see what a small little chunk of the soil organic matter actually is. It's really a very small part of most soils. Most of the soil is made up of minerals and then air and water. We do have some muck soils in Vermont and other soil types that are, far more organic material. But in general, we're looking at a very small but highly influential component of the total soil volume. Okay, so again, we're managing or wanting to manage about 5% of the soil volume with the different practices that we use. It's kind of the thing a little bit that we have control over, right? We don't have a lot of control over the kind of mineral makeup of the soil, but we do have more control over the organic matter makeup of the soil. And that organic matter then can also influence the amount of air and water in the soil as well. So even though it's a small piece, it's very influential in the soil. And we also have the greatest influence through management of that portion of the soil. Okay, so organic matter, again, we can influence with management, but kind of the baseline organic matter that we have, is really influenced by climate and the soil type, how the soil was formed. So the Northeast in general has relatively high organic matter levels. So if we're comparing ourselves, let's say, to the South, we have much higher resident, organic matter levels because of our climate, and the vegetation that we have because of our climate, and the environment that we have. Okay, and so when it's colder, we have less turnover of organic matter. So where it's really, really cold, we have very low inputs of organic matter, but we also have very low output of organic matter. It cycles very slowly. And we're kind of in the middle, where we have, a somewhat warm climate with cold conditions. So we get good vegetative growth, which increases organic matter levels. And so we have relatively high organic matter levels in the Northeast because of that. Now, as far as our potential to improve or maintain what was there originally or improve through our farming practices, that's where our management really comes into play. So we can change soil organic matter, like I said before, but that's up to us. Okay, but we're pretty lucky in some respect because we're already starting with levels of organic matter that we consider relatively high. So what is that? It's like 5%, and in some cases around Vermont, 8%. So again, a lot of that has to do with our climate and the soil types, and soil forming factors and our topography. But a lot of that also has to do with our current land use, and how we manage. So, again, if we look to the south, a lot of the organic matter levels there are much lower. And again, it has to do with heat, soil type, topography, etc. But what we're really going to focus on is what we do have an influence over, our management, and how we choose to manage our agricultural soils in particular, so that we can optimize organic matter levels. And as I said before, hopefully improve our farming systems, but also the environment around us. So I think by now you probably have heard, I'm not sure how many times, that soil organic matter is a really significant driving force in the soil itself. And it influences all aspects, the chemistry, the physical aspects of the soil and the biological. So it's important to spend a good amount of time on it. And it sounds like, there'll be a strong focus on managing, building, and understanding soil organic matter. And the reason for that is, again, we can have an influence over that, and it's really critical to the overall function of the soil. So again, lots of different aspects of the soil that organic matter influences. I mean, this is actually kind of I don't want to say it's a short list, but we could dig into each one of these for hours. But organic matter influences nutrient availability and nutrient cycling, aggregation and soil physical properties, the storage of water, the diversity and activity of the different soil organisms that we have, the color of the soil, the presence of different growth stimulating compounds. And it's also, essential to global cycles, carbon, nitrogen, and water. They're all strongly influenced by soil organic matter and the cycling of it. And of course, I feel like we hear about this a lot more today because, of our concern around a changing climate and global warming and the impact that carbon and carbon emissions and nitrogen emissions have on climate and global warming. Okay, so again, organic matter is a very small fraction of the total soil mass. And that fraction is really complicated. And, Fred, Dr. Magdoff, who you heard from a couple of classes, maybe 3 classes ago, really tried to take the complexities of soil organic matter and really simplify them for all of us. And he says it in his book too, which is now, I don't know what edition is. I have 3 editions sitting on my desk, by the way, that I was referring to. 4th edition. Okay, the 4th edition, I thought might get rid of some of these kind of really basic things and start digging into like mineral associated organic matter and different topics that we hear a lot about. But he kept it simple still, and I think we should do that too. And I'm going to dig into each one of these fractions a little bit, but it is complicated, and not that I don't think you can handle it, but I just don't know how much time we actually need to spend on all the gory details. I think you need to understand the high level pieces of organic matter so that you can help people make decisions on their farms or for their farms where it's really important. So most of the organic matter that is in the soil is in what Fred calls the very dead fraction. And we often refer to this as humus, but now there are new terms for this, in the last probably decade or more, called mineral associated organic matter. But still, this terminology of humus or kind of microbially protected organic matter is still easily classified as very dead. And so most of the organic matter, 60 to 80%, is in this very dead fraction. Okay, and then we have the active fraction, which is what Fred calls the dead, or kind of recently dead. It's not very dead. And that makes up 10 to 20% of the organic matter. And we call that the active fraction again, because it's recently dead and microbes are able to decompose it and turn it into humus. So we'll get into that a little bit more. And then we have the living fraction of organic matter, which makes up, again, 10 to 20% of the total organic matter. And I'm not sure I need to describe the living all that much, but, it includes roots and microbes and even bigger organisms, all working to break down active organic matter to live and thrive. And then that becomes the dead. So the living eats the dead, that then becomes the very dead. So it's pretty simple, but again, we can break it down and make it even more complicated. So one thing I wanted to touch on, and I actually was just sent an email about this morning, is what's the difference between soil organic carbon and soil organic matter, because we all seem to be very, very interested in carbon these days, right? And sequestering carbon and more carbon in the soil. And we're not necessarily saying we want to sequester organic matter. So are they the same? Are they different? And I just thought we should clarify this a little bit. Soil organic carbon is a component of the soil organic matter. Okay, so it is part of organic matter. And a rough estimate is that organic matter is primarily made up of carbon. It actually carbon makes up 58% of organic matter. Okay, so what's the rest? Well, it's water and nutrients, right? So we know that organic matter that we're putting into the ground is more than just carbon. So if you just think about it that way, if you're taking a cover crop and you're incorporating it into the soil, you're not just incorporating carbon, but the majority is carbon. So they're not one-to-one, okay? There's a lot of conversions that are used when people are trying to figure out, oh, how much carbon is being stored in that soil. Well, we know the organic matter level. Can we make that conversion? And you can, but the scientists, again, will argue that that's not accurate, because there's more carbon in the soil than organic carbon as well. So, for what it's worth, organic matter and organic carbon are not the same thing. Okay, soil organic carbon is a part of organic matter, and it makes up most of the organic matter, or at least around 50%. Organic matter is even more complex than just being carbon. And, obviously it's living material. And living material is made up of more than just carbon. All right. So here we go. We're going to go through each fraction. So we have the living, the dead, and the very dead. So let's talk briefly about the living. Oh, wait, I should go back to this. And I already said this too, that the living, right, becomes the dead, and the living eats the dead, and then eventually the dead and the living become very dead or stabilized organic matter or organic carbon. Okay, so we're going to go through each step, kind of show you and walk you through how that happens. And again, it's not that complicated, but as scientists, we really dig into it. Okay, the living, this is like not a complete list, obviously, but just to make sure people know when we're talking about living organic matter, we're not just talking about microbes and things we can't see. We are talking about other organisms as well, like moles, springtails, protozoa, nematodes, plant roots. So it's not just microbially active, which is a lot of what we measure when we measure biology in the soil. It also includes larger organisms too. And those larger organisms are just as essential as the ones we can't see. So we don't want to forget about them. And some of them are real indicators of soil health. And I learned this the other day, which I thought was fascinating. If anybody watched the Neonic webinar series that we put on, there was a speaker talking about the impact that these pesticides are having on springtails. So springtails you actually can see those. They're almost translucent when you open up the soil. You kind of see them hop a little bit. That's why they're called springtails or collembola. And they're really important. They're actually like fungi farmers. And so what this speaker was saying was that these pesticides were killing the springtails. And because the pesticide was killing the springtails, there was actually less fungi that were helping to create soil aggregates, that then they were actually seeing a depletion or a reduction in aggregate stability. So all of these different organisms are really critical, often to each other as well. So again, just to take this basic view of it, and I feel like we all say that, oh, the microbial activity. It's more than that. And so I think we just need to keep that in mind And I'm not, somebody else is going to get into soil life a lot more than I am. But again, it is a component of the organic matter and a very important one. So I just, want people to think about it a little bit more than just microbes. Um, we have to have often the bigger organisms that chew up and make pieces of living organic matter, like plants, and sometimes dead organic matter, like you see this cow patty here. We got to have dung beetle, let's say, that sort of takes some material and starts to break it down or to bring it down deeper into the ground. So again, the living component of organic matter is really critical to the whole system, and the diversity is really important. We often really mostly I feel like talk about earthworms, and maybe because they're so visible, but again, not to underestimate ground beetles, dung beetles, and all the other organisms that are really important to cycling organic matter and making that transition from the living to the dead, and the dead living eating the dead, and then forming the very dead. And that's the part of organic matter that we're really trying to increase to build stable carbon in the soil. So all of these pieces, again, really important. Okay. So with the living, we have a lot of interesting relationships, again, that we're not going to dig into. Hopefully the person that covers soil biology will really get into some of the fun and interesting things that happen below ground, but there's nothing more that is sort of delights me than these fungal hyphae nooses, the strangled nematodes. So it's kind of a crazy world down below our feet. And I think really for most producers, just knowing that they're building that diversity of organisms is really important, and maybe a little bit less important about specifically what's there, but knowing that we're building an environment that is conducive to that bigger diversity that I was just talking about. That's, at least for me, the message that I send home to the farmers. So I wanted to talk a bit about measurements because everybody is really into soil health testing. I know Lindsay talked a little bit about this last week. Measuring living organic matter is it's expensive and it's difficult often to interpret, especially at a farming level, but even at a scientific level. There are lots of ways to do this, through DNA analysis, through an analysis that you may have heard of called PLFA, or phospholipid fatty acid analysis. There are new analyses where people are just looking at different kinds of nematodes or other living indicators that we know contribute to soil health. But they're really expensive. The soil DNA test is a couple $100 a sample. The PFLAs are over 100. The nematode analysis is a little bit less expensive, but still $60 to $70. So really, measuring the actual living can be very expensive, and it's very difficult to do, especially microbes. And it's really difficult, I think, to interpret it as well, especially on a very practical level. And what does it mean to my farming operation? So I just got off a soil health call actually with a bunch of scientists. And that's what the scientists are saying. This is the hardest thing right now, is taking these indicators and measurements and making them practical. Like, what does all that mean to somebody out on the ground? But I want you to know, and you probably already know this, that there are ways to measure. But at this point, many of these measurements, again, are really expensive and really difficult to interpret it. So it's not necessarily something that I'm recommending for people to do at this point, at least on the ground. But it's there, and you can get results back and try to interpret those for the situation. I think using visual observations is, your eyeballs is really the best measuring tool that most of us have as far as above ground organisms go, and even earthworms, and just going out there and seeing what's living. But again, getting down to measuring individual organisms, we're just really not 100% there yet on a really practical level, but I hope we can, have more of a discussion around this. Okay, so there's the living and then there's the dead, and the dead it's recently dead. And recently dead, actually, you'd be surprised, recently dead is 0 to about 50 years. That's recent. Okay, so that's what falls into this category. So something that just died, or something that's actually been kind of dead for about 50 years. That's what we consider in the dead pool. So recently dead soil organisms and crop residues, and also above ground organisms as well, that provide the food, so the energy and the nutrients for soil organisms to live and function. So we also call this the active fraction. And I know like many of you are familiar with this term, active organic matter. And that is measured on the Cornell soil health test. And there's different measurements for that I'm going to talk about, okay? So the active fraction, it's easily decomposed. It's what the organisms in the soil are chewing on, or the above ground organisms are also chewing on and breaking down and cycling. They're using it to grow and thrive. And then also they're producing wastes, etc., that then allow our plants to take up nutrients and grow and thrive. So the active fraction, again, is recently dead, but that encompasses a pretty broad range of time. And again, that's about 0 to 50 years. Most active organic matter, you can still actually kind of tell what it is, especially the more recently dead, right? So within 5 years, if you start separating it out of the soil, and that's what this is actually what we call POM, particulate organic matter, and I'll talk about that in a minute. So POM is a measure of the active fraction of organic matter. And like I said, if you took this out of the soil, removed it, you'd see that it sort of still resembles plant materials, or maybe even animal parts or materials, okay? So, and you can see it's also this kind of light brown color. And again, this is very representative of the active fraction. It comes mostly from plant material, but obviously some animal material as well. And like I said, the living eat the dead, and that's how these materials are cycled and broken down over time. And that's also how nutrients are cycled in the soil, and we'll talk about that more in a minute. So the living eat the dead, and they eat the dead, and then they kind of keep eating it. And different organisms eat different parts and different fractions of the dead. So again, it's not simple. So how do we measure active organic matter? And I think most of you are familiar with these, right? So we measure active organic matter through we can do a physical measurement of that, which is a measurement of POM, which is the particulate organic matter. We can also measure kind of using chemical analyses, permanganate oxidizable carbon. That's what's on the Cornell soil health test. There's also another measurement called water extractable organic carbon. And then we also measure the active fraction by measuring respiration, okay? And a lot of people would say the respiration is a measurement of the living. Kind of. Yes, it kind of is. But it's more a measurement of what active fraction is available for the microbes to eat. All right, so these are the measurements that are really common. Again, we see them on the Cornell soil health test. especially permanganate, carbon, and also respiration. So again, particulate organic matter is organic matter that is greater than 53 micrometers. And it seems kind of odd that we just set this range, but anything less than that is actually considered stable organic matter. And so within POM, so POM is physical fractionation. So we actually pull that out by floating it on top of a dense liquid. And in research articles, you would also see this called the light fraction. And again, it's really about a physical separation. It's densiometric. And you can float it out using this kind of dense solution, and then you can separate it and weigh it and measure it, put it under an electron microscope. But that is particulate organic matter, and that is considered the active fraction. That fraction actually contains the permanganate oxidizable carbon, the water extractable organic carbon, and respiration. Now I say it contains it because POM is kind of all of it. And when you use these as other measurements, you're only getting a piece of the POM, a piece of the pie, right? So permanganate oxidizable carbon is the amount of carbon that's oxidized or eaten away by a chemical solution in 10 minutes, right? So it's measuring a part of carbon that can be processed theoretically by microbes in 10 minutes. So it would be what is really recently dead, okay? Same with the water extractable organic carbon. Remember I said the time frame here is 0 to 50 years? If it can be broken down by this chemical reaction in 10 minutes, it's not 50 years old. It's relatively new. And when we are measuring respiration, it is microbes that are eating, okay, the microbes in the soil, usually for most measurements within 24 hours, okay? They're eating the active fraction of organic matter that they can get at very quickly in 24 hours, and it measures the amount of CO2 they're respiring. So the permanganate oxidizable carbon, the water extractable carbon, and respiration all are measurements of active organic matter, but they're of the most recently dead. And if you add those three up, okay, because they all are kind of going at different pieces, it's not equal to the amount of POM in the soil. All right, so again, all these measurements that we can do are indicators of active organic matter. And the reason the bottom three have been chosen by labs like Cornell is because they respond to short-term changes in management. Now, hopefully these the wheels are starting to turn for you about everything you've been learning. Okay, so if somebody starts to use a cover crop and they take one of these measurements and they've just recently incorporated it, permanganate oxidizable carbon measurement is probably going to pick that up. And so isn't respiration, because it's really new stuff, okay? But if you measure POM, which is a lot of stuff, 0 to 50, okay, years old, you may not see that change in somebody's management as easily. So that's why, places like Cornell and some of the other labs, like Ward Lab as an example, they use these other measurements because they're really picking up that very new organic matter amendment that farmers have done, okay? And that's kind of what this table is showing below, which is kind of complicated, but I just thought I would put it there anyway. To the left, it's the percentage of soil organic matter pool. So this is saying, you know, in a grass pasture, the percentage of the soil organic matter that's in the palm fraction is 11% or 12% roughly. And then the fraction that's in the pox is 1.7. So it's breaking it down. Now, if you go over to the right, you can see the percentage of those more, those active carbon measurements that are more responsive to recently dead. You can see they only make up a small percentage of the total palm fraction. So this has gotten complicated really fast, right? We went from just saying it's dead to then dead now means what? You know, there's a whole continuum of dead. And there's all these different ways to measure that. And again, it really comes down to what is it that we want to know about that field or that soil or what that farm is doing. And in most cases, we want to know, you know, is the shift from no cover cropping to cover cropping or no till or till to no till, is that changing the soil organic matter in some way in the short term? And the easiest way to pick that up is by using one of these measurements of the active fraction, but they are all looking at different things. But so complicated again. I went from simple to complicated, but I hope that as you're looking at those soil health tests and you see permanganate oxidizable carbon, and then you also see respiration, it will help you start to understand why those values may not line up. Why might it be high in respiration, but low in permanganate oxidizable carbon? So the carbon quality is really important to how high these measurements are. Okay, let's move on to the very dead. And again, should be simple. Okay, so now we're talking about 50 to 10,000 years old. That's our time frame here, maybe older. Okay, so they're very well decomposed organic materials. They're often referred to as humus. Okay, humus gets used in a lot of ways, but it, you know, is meant to describe stable organic matter, stable carbon in the soil. Now we've started to see another term quite often. Like I said, it didn't make its way into Fred's book. I was a little surprised because it's everywhere in the scientific literature, and I'm also starting to see it in, you know, extension literature. And this is mineral associated organic matter. And that is stable carbon. And I'm going to get into this a little bit more so that hopefully you can understand it. All right, so this is a picture of stable organic matter. This was actually separated out of the soil at the same time as we separated the light fraction. Okay, so this is through a densitometric fractionation process as well, along with using centrifuge to spin it out. I don't, as far as I know, I'm not sure if you can get a measurement of mineral associated organic matter for your soil commercially. I haven't found anything, but you know, that's how I have separated out stable organic matter, is basically using a physical separation to be able to do that. And so you saw the light fraction of the soil, and now you're seeing the stable fraction, the stable organic matter fraction. And you can see how different it looks, right? It doesn't look like plants. It looks black. It's very dark. And you don't really see anything like identifiable in there. And that's the way it should be, because it is old, it's been used by the microbes, and it's been converted basically into primarily, not all, but primarily a lot of carbon. Okay. So we can call this stable organic matter. We can call it humus. But however you want to refer to it, basically it's material that is protected from further microbial decomposition. And it could be protected, just because chemically there's nothing else there for the microbes to get at. It could also be protected from decomposition because it's attached, like physically separated from microbes. But it generally has been decomposed to a point beyond which microbes will be able to utilize it any further. Okay, and then we call it stable. Now, it does have very conducive and important physical and chemical properties in the soil. So the active fraction primarily kind of feeds the living. It does some other things too, but the stable fraction helps to create a lot of charge in your soil. It also helps to create small aggregates. It also helps with water storage. It also stores a lot of nutrients. Okay, so even though it's chemically not conducive for microbial decomposition, there still can be a lot of nitrogen in particular left on these carbon compounds. Okay, humus also can surround nasty chemicals and kind of keep them out of water. And again, helps to retain nutrients because this tends to have a lot of negative charge on it. So when we hear, organic matter can increase cation exchange capacity, it generally is referring to more stable organic matter. Okay, so soil color and organic matter, you can see where that color comes from. It's the more stable fractions. It's the dead fractions of organic matter. And so the more organic matter, especially total organic matter that you have in the soil, you can see the color will become much darker over time. And so when you go out and you see a really dark soil, you usually know that it's had many years or some type of management that would be conducive to building more stable carbon in the soil. Okay, so let's wrap this part up, and maybe that's the whole, took longer than I thought. Okay, so we have the active fraction of organic matter, and here it says fresh residues, but I've already told you that this can be over a pretty broad continuum. Okay, so we have the fresh residues, we have soil organisms, biomass, and metabolism. So basically the organisms are working on the residues, right? Over days, over months, and over years. So this is not a short-term process. And the microbes that start here and the soil organisms are really different than the ones that are working on the residues years later, right? Because you can imagine that you have a leafy green plant. What's the first thing that's going to disappear? Okay. What's the second thing, the third thing, the fourth thing? Like the easy stuff goes first. The sugar, the non-structural carbohydrates, and what goes last? The lignin, the cellulose, right? The components of the plants that are much harder to decompose. So over time, that will happen, but it doesn't happen instantly, and it doesn't happen by the same organisms, okay? So the organisms are incorporating the nutrients, carbon into their biomass, And some of this is also being respired off, some of the carbon as CO2 during respiration, during the decomposition process. Okay. And over time, and then you see decades here, we get stable organic matter that becomes fixed to soil particles. And that's what we call the mineral associated organic matter. Okay. It's not always just carbon. It often has nutrients with the carbon. Okay, so there can be a lot of nitrogen in mineral associated organic matter and other nutrients too, and other compounds too. So that becomes fixed to the soil particles. And again, it's referred to as mineral associated organic matter. What I want you to see here is this protection in aggregates. And that's another really important fraction of organic matter that we consider stable in the soil. And I'm going to talk to you more about that. But it becomes unstable if the aggregates get broken. So what is truly stable is the kind of the organic matter that gets fixed to these soil particles, that is mostly highly decomposed and has originated from the soil microbes themselves. Okay. Woo! All right. So here's a picture
Hey,
of
Heather.
that. Yeah.
Heather, we do have a couple questions. If you have
Okay.
a second.
Maybe let me finish this one slide and then we'll kind of wraps up this
Okay.
whole piece. All right. All right, so this just sort of
Perfect.
summarizes what I'm talking about here, where we have pieces of decaying plants and animals. Okay, this is what we call the particulate organic matter. This is fast cycling, and again, that's 1 to 50 years, 0 to 50 years. So the lifetime of palm is short and long, so you can start to see the different practices and things we're doing, where it fits along that continuum. All right. And then how we would measure that. So it's interesting that the carbon to nitrogen ratio of palm is actually more carbon than nitrogen. And it's still pretty quick cycling. So the mineral associated organic matter generally are it like originated from microbes, right? Breaking down that palm over time, incorporating it into their biomass, and then essentially ending up themselves as very stable carbon and primarily nitrogen attached to soil particles. So you can see that this lifetime is 10 to 1,000 years, and the carbon to nitrogen ratio is actually quite a bit different. There can be a lot of nitrogen on mineral associated organic matter, and that can be quite a reserve for the soils. All right, so now we can take a few questions.
Thanks, Heather. This is from one of the earlier slides when you're referencing that the soil organic matter is like 3 to 5%. And the question is that in the first 6 inches of the soil, or does that go all the way down?
No, that would be in the top foot.
Top foot. Okay.
But not,
and then
when you say all
sorry,
the
go
way
ahead.
down, I'm not sure what that means, but it would definitely change below a foot. Yeah, that is,
Okay.
that's something we struggle with, is how to get organic carbon deeper into the soil profile.
Then I've got another question. Is there such a thing as too much organic matter?
So if you read the chapters in the Building Soils for Better Crops, Fred does go through and talk a little bit about saturating the soil with mineral associated organic matter. So there's only so many places, kind of like when we talk about CEC, there's only so many places where things can bind to the soil. And that's the same with, organic matter. So we can actually reach a saturation point in the soil for mineral associated organic matter. However, we can keep building POM, right? It's just where does everything else go? It's not going to stay in the soil. So we can saturate the soils, you know, and that actually is a concern. I just never thought this would be a concern of scientists who are trying to figure out how to sequester carbon. Are we going to saturate the soils? And I thought, really? So is there too much? Yeah, I think definitely, you know, we can artificially create situations that make a little bit of a mess, especially environmentally. I see this a lot in maybe high tunnels, you know, really small areas where people are adding a lot of organic matter, and not thinking about, you know, too much, like nutrients, lots of, so there can be issues, yes.
Okay. And then I just had a couple questions. You said that the palm is about 58% carbon. Is the mineral associated organic matter also 50%, 58%, or is it different?
When I said that, I'm talking about the organic matter as a whole. So that would include all of the fractions.
Okay.
Yep. I mean, and again, that's
Okay.
like
And
the scientific standard, but every soil would be really different. Not really different, but you know, that's the estimate that's used.
okay. And then just one more clarifying question. So when I get a soil test back from the UVM lab and it says organic matter, it's telling me about the palm or the all the living dead and very dead.
Yeah. So the soil organic matter measurement that's given to you is total soil organic matter. So it includes the living, the dead, and the very dead. And generally, it's determined by combustion, essentially. And that's why, you know, when we look at total soil organic matter, and then we want to make a change on our farms and we go out and do it, and sometimes even for 5 years, you go and take another test and you don't see any difference in soil organic matter. And you think, oh, is all that for nothing? But really, you're increasing likely the POM, which is a small fraction of the total organic matter. So it's harder to pick up in the total value, which is why people have started to measure these active pools so people can see those differences.
Wonderful. Thank you, Heather. Those are all of the questions for right now.
Okay. All right. So I just wanted to summarize this a bit. So the active pools of soil organic carbon can be determined many different ways. Okay. And they all will give you different results and are really measuring different types of carbon along, or different types of quality of the active carbon pool, or active organic carbon pool, active organic matter, sorry. So if you're making like cover crop or tillage changes, measuring that active pool, especially pox and respiration, are going to help you see differences in soil organic matter. So the mineral associated organic matter is microbially derived, and POM is generally plant derived, but they're all part of a system together, right? So POM is the energy source for the microbes, which increases the mineral associated organic matter, which in turn supports plants and inputs that they need. So it's all one big cycle. When you put it all together, that gives you the total organic matter, and we can separate out all the different fractions as well. So if you're trying to increase stable carbon, which is the mineral associated organic matter, then we're promoting carbon dense, long-term carbon stocks while enhancing organic matter nutrient content and overall quality. So I think, when we're talking about building soil health basically is building soil organic matter. We're talking a lot about adding active carbon to basically improve microbial activity that also then drives kind of this long-term stable carbon so that we can be sequestering more carbon. So our efforts to improve soil health help us ultimately build more soil carbon and long-term carbon storage. Okay, so let's talk a little bit about what these different organic matter fractions do in the soil. They all play really important roles, and we've talked about that, but we'll get into a little more detail as well. And this is right from Fred's book, all the different things that organic matter does. It feels like the cure-all. So, we've talked about a lot of these, holding water and cycling nutrients and promoting biological activity, protecting us from harmful substances, suppressing diseases, all kinds of things. And ultimately, this hopefully is leading to healthier plants and higher yielding plants and more resilient soil. So as I started saying, soil organic matter is really at the heart of soil, the physical, biological, and chemical properties. It's a driving force for all three, and kind of, connects them all. So the active fraction and the living fraction help to create available nutrients. It helps to cycle nutrients throughout the system, not just for plants, but also for the biological community itself. And again, there are lots of different organisms that play a role in this. It happens right from the time, a plant residue is put into the ground, all the way to years later, where we still have organisms trying to break down cellulose and lignin. Okay. So the living eat the dead. And again, as a result of that, the nutrients that were once living get released into the environment to be utilized by the organisms that are breaking them down to continue to thrive and grow and build biomass. So I think, the nitrogen cycle is a really good example of that. And again, this came out of Fred's book, where we have crop and animal residues making their way into the soil. And we have a process called mineralization, where microorganisms are breaking down organic matter from the plant residues and freeing up available nitrogen. And that available nitrogen, again, can be used by other microbes or can be taken up by plants that are growing or can be lost into the environment, right? So again, if you're thinking about the plants that are growing and why we harvest them and eat them, or why we harvest them and feed them to our livestock, it's because we need to get what? Like energy, protein, and nutrients. So if we're not taking those and feeding ourselves or feeding animals with it, and the residue is going back into the ground, the same thing is happening there. Now, when we have animal residues, manure or residues that are made from plant residues and animal residues, like let's say compost, it's essentially the same concept. We're taking these materials that have lots of nutrients, carbon, and energy, and other organisms are feeding on them, building their own biomass, and their wastes are being utilized by plants. I mean, essentially, that is the cycle. So organic matter is critical to nutrient cycling, feeding the microbes, and making those nutrients really move around in the soil. I know we don't have a ton of time to go into that, so we can go back to it if we need to. So the very dead, again, and that mineral associated organic matter has a lot of charge on it. It also has a lot of nutrients, but it's not recalcitrant, but it's more slowly available, right? Because it's not like the microbes themselves are going in there and continuing to chew on that material. It's becoming released through more chemical processes and less biological at that point. But it also has a ton of charge on that mineral associated organic matter. I mean, more charge than clay has, really. So the more stable organic matter you have, the more cation exchange capacity that your soil will have as well. And if you have a sandier soil or a lighter textured soil with very little clay, you'll have a lot of your charge that comes from the soil organic matter. So building stable organic matter in sandier soils and lighter texture soils is really important because it helps to increase the cation exchange capacity and the soil's ability to hold on to nutrients. And I'm sure Lindsay covered that in the last class. She was talking about soil tests. So again, that stable organic matter gives you a lot of charges, more even than clay. Clay has a lot of negative charge, but stable organic matter has far more, and I mean 100 times more, if not more than that, in its ability to hold on to nutrients. It also, is able to hold on to other elements as well, and other materials in the soil, different, not pathogens, but contaminants, and keep them, stuck to the soil so they're not making their way into water or the environment. Okay. All right. So soil organic matter also plays a significant role in building soil tilth or soil physical structure. And, this is really critical, especially in the conversation around climate change and more erratic weather conditions, because we want to build a soil that is able to absorb water, drain water, hold on to water. We want to build a soil that's able to protect microbes and build healthy populations of soil biology. And all of that building of soil tilth is really driven by organic matter and biological life. Okay. So when the living eat the dead, they start to form these aggregates. So when the living eat the dead, it's messy. It's gooey. You think about earthworms as an example with the slime on them. You think about the rhizosphere and roots have a lot of exudates as well. Bacteria have a bunch of, sort of these gels, and there's fungal threads. So when the living eat the dead, it becomes really messy, which is great. We want it to be messy. And what happens is we start to get the production of these glues and this stickiness, and all the different portions start to get stuck together into little aggregates. And then the little aggregates get stuck together into bigger aggregates, like when you have roots growing through them, as an example. And this formation of aggregates of all different sizes is what creates a really healthy soil with good physical properties. Now, often what happens during that process is that we get organic matter that is active stuck or glued in between soil minerals. And this is called occluded organic matter. it's probably hard for people to believe this is really this complicated. It is for me sometimes. But within a macro aggregate, you can get occluded organic matter that gets stuck in there, and it's protected from microbes. So it's considered stable. Okay. And so this can be a really big portion of the stable organic matter in the soil, which is all this active or, you know, yeah, I guess the active or palm fraction getting stuck in these aggregates that soil microbes can't necessarily get to. All right. And this, again, is an important piece of stable organic matter. So if we look at this a little more closely, here's an aggregate that's blown up. And you can see what it's composed of inside. You know, you have fungi and bacteria and sand particles and roots kind of all glued together, forming this aggregate that still has some pore space in it. You can see there's a little bit of water in there, room for air to get through, and microbes to live. So you get these small aggregates that then start to build bigger aggregates that then start to build this structure that becomes relatively unorganized, which is exactly what we want. So here's, I really like this picture of a macro aggregate so that you can see the composition and complexity of the aggregates that we're trying to build. So we have micro aggregates, which are these kind of oblong and circles. And these contain clay, and they contain plant and fungal debris and different silt and other materials that are building tiny little micro aggregates that then get encased with more mycorrhizal fungi, more particulate organic matter, and plant roots and glues and goos into a bigger structure. And these aggregates, micro and macro, are really critical to the physical processes of the soil. So you can see once we have all these different aggregates and different sizes, the soil has a better ability to infiltrate, allow the infiltration of water down through the different size aggregates. So you can see here with a rainstorm where you have small and large aggregates stacked on top of each other, there's more area for water to flow through the soil versus next to it where we have soil that's not aggregated, right? And we get a rainstorm and there's no ability or very little ability for the water to make itself through these kind of single minerals stacked on top of each other. So from an environmental perspective and a climate change perspective, having these aggregates is really critical to soil drainage. And you guys have seen this probably a million times. And we did this at the in-person training where we were looking at, you know, the stability of aggregates and pouring water through them, pouring water through soil managed in different ways and looking at if it came out clean or if it ran off. And really that all has to do with the aggregates in the soil and how stable they are and how diverse they are. This is really important to microbial and plant health. And, you know, this picture, I think, simply says it all, where you have a well aggregated soil to the right that has space for air and water. So, you know, there's air for the plants to grow and the microbes to grow. There's water for plants and microbes to the right, and then to the left, where we don't have that same structure. There's just an inability for air to really move through the soil and also water. So that leads to more runoff, can lead to more denitrification and emission of greenhouse gases. And then obviously it can lead to poor plant growth as well. So this concept of aggregates, building aggregates, is really, really important aspect of building organic matter for our farms. Okay, let's talk about water retention and management. And that has to do with creating these pores and aggregates in the soil. But soil organic matter, it increases our ability of a soil to basically receive more water, like I just showed, and also to hold more water, okay? So it's kind of like a brick versus a sponge when we're talking about that porosity, okay? So think of a sponge and all the different pore sizes. That's what we want our soil to be like. And those pore sizes are created by having those different size aggregates organized or not organized throughout the soil. All right, the palm, which we've talked about a lot, serves, as this kind of low density bulking agent, kind of similar to a sponge. So the more palm you have, you're sort of bulking up the soil with a lightweight material that basically allows for more absorption of water. So it helps both create and maintain larger pore spaces and channels. Now, that mineral associated organic matter is what really helps to build the micro aggregates, right? So palm helps to build the bigger aggregates, and the mineral associated or stable organic matter helps to build the smaller ones. All right, so when you have all those large pores, you're going to infiltrate and drain water better, okay? And the small pore spaces are what's going to hold on to water over the long term. So during a rainstorm, if you have the bigger pores that are mostly created through palm and microbial activity, then you're going to have better drainage through the soil. You also need to have the small aggregates and the small pores to be able to hold water in these little crevices so that when it gets dry, you're able to suck water out of those little pores. And that's what builds resiliency when it's really wet or resiliency when it's really dry. And then, of course, organic matter on the surface is critical to help reduce compaction, runoff, erosion, etc. Okay. I thought this was a really great way to show available water with increasing organic matter content. So you can see based on the soil type, the more organic matter you have, the more available water you will have, right, during dry periods, which is really important. Now, the other graph to the right shows you additional days of available water content by soil organic matter and texture based on corn daily usage. And again, you see kind of the same trend. With more organic matter, you have more days of available water at the level that corn would need it in its daily usage, which is about a quarter of inch of water a day. That's a lot of water. So the more organic matter you have there, the more days you have where you'll have that available water. So just thinking about, going through a drought, this is the type of organic matter levels that we need to help keep our crops healthy and growing as the soil becomes extremely dry. Okay, so again, soil organic matter is going to protect us when it's dry, but also help us drain when it's really wet. I wanted to briefly talk about disease suppression because there were questions about that. And disease suppression from organic matter is really cool, but very complex. And I think most of the disease suppression that we see is from the active fraction. So by adding active or adding new organic matter and keeping the general population of microbes very active can suppress disease pathogens. Okay. And it's more about competition for resources and space than it is thinking about any specific microbe. So organic matter mediated disease suppression, which is what it's called, is general suppression. So you add organic matter to the soil, and generally, if you're maintaining populations microbial populations and you have a microbial active soil, you can reduce the impact of many common plant pathogens. And it's way more complicated than that. We don't have a ton of time to talk about it, but this slide shows a really good example. This is a very old example, but probably the most written about, like disease suppressive story. And, you know, they looked at the soil that was managed in a certain way where they were adding organic matter back to this system. And to the left here, you see this ladder, and that is verticillium wilt that was killing, in this case, it was avocado trees. But you can see where they started adding organic matter back to the soil. You can see that you can still see the ladder, but it is completely overtaken by lots of other microbes. And basically, increased microbial activity outcompeted the pathogen in space, time, and nutrients, and overall was able to keep the levels low enough that the plants were not impacted by the pathogen anymore. And Cornell used to measure this. They don't. I think you can ask for it, but you can look at disease suppression in your soils, but I think you have to ask for it at this point. Just keeping track of time and wondering if there's any questions at this point. Lauren.
There is one question, Heather.
Mm-hmm.
One of the exercises in our fall workshop in Richmond revealed that soil organic matter also has anion exchange capacity.
Mm-hmm.
Could you elaborate on that relative to leachable nutrients?
Yeah, the anion capacity or exchange capacity is much less in soils. It's also organic matter can have anion exchange capacity. Certainly more organic matter, of course, can help retain more nutrients from that respect as well, but still a very, very small fraction of the overall kind of exchange capacity as a whole. But yes, building one will build the other as well. I don't have an exact number though.
Thanks, Heather. That's the only question right now.
Okay. Maybe just a little bit more on disease suppression, mostly because I spent a lot of time working on that myself. And, you know, it is really important, and especially in vegetable systems, but even in corn systems. And I'll just show you this. This was actually in sweet corn, but you can see these two soils. And we were adding compost to these soils, and it was dairy manure that was composted, and we were adding it at low and high rates to soils that had a lot of root rot pathogens, and you know, we're killing and wiping out entire fields of sweet corn. But they were fields where they were not adding any organic matter back. Everything was driven by chemical fertilizers. And part of the reason for that was like food safety. And it's really interesting to think about these, you know, just these different ways to look at things. And sweet corn farmers were not adding manures to their fields. They definitely weren't composting either, or cover cropping, but they weren't adding any manure amendments because they couldn't meet food safety standards if they did that. And really what was happening were these soils were so depleted in organic matter, just allowed this group of pathogens to kind of take over, right? And it was killing sweet corn growers financially. So we did go in and added, and again, in this case, it was composted dairy manure, and we could immediately see reductions in disease by doing that. And it really had to do with enhancing the overall biological activity of the soil. And the pathogens were pretty weak pathogens to begin with, but they didn't have any competition. And so they were able to just live and thrive. And when their host showed up, the sweet corn, they would just attack. And so we were able to control that disease by thinking about how do we increase organic matter amendments. And then there was a whole host of other benefits to the farms. So just an example, I guess. All right, so let's wrap up talking about building organic matter. And this can't comes out of Fred's book directly. If you got to add it, if you're removing it, um, we have been pretty good at adding organic matter in Vermont, and mostly because we have livestock predominantly, or have had predominantly livestock operations. That makes it relatively easy. We also have a lot of perennial forages and perennial cropping systems because we have a lot of hay and pasture ground. So we can, have a little bit easier time, I feel like, in maintaining and adding soil organic matter. And as a result of that, our levels in Vermont are higher than around us. Our average organic matter levels, like I said before, are over 4. And we see even higher, but compared to New York, compared to Pennsylvania, they're all down in the 3% range. And, again, part of the reason we have higher organic matter levels here is because we have a livestock-based farming system, and that allows us to add organic matter pretty consistently. Now, our losses, again, when we have hay and pasture, are relatively low, but in our annual crop systems, we do see a lot more losses, especially if we're tilling, or mostly if we're tilling, and also if we're removing more than we're putting back, which is, pretty common. So how do we continue to maintain and build organic matter in all the different fractions, right? So it's not just about building the living or building, the dead or the very dead. You saw it's all a cycle. But, it starts with adding food for the microbes, and different types of food. So we have to consider both the quantity and also the quality of what we're adding to the soil. So just adding one type of amendment all the time may not be the best, right? So putting a little thought into what we're trying to accomplish over the long term may change how we view what we want to add back to the soil. We have to build a strong house. So we're going to feed microbes, but we have to have a strong house for them to live in, but also for our plants to grow, right? And that's really thinking about building those aggregates and the diversity of aggregates that are there, both, in size, shape, and also what they're constructed of. And then we need to try to create systems that are free of drastic change, which is hard during the sort of erratic climate that we've been experiencing. But drastic changes also mean things like tillage. Okay, so trying to reduce tillage is really, really important when we're trying to build organic matter in all the different fractions. And again, I kind of end on quantity and quality of organic matter because that's really important to how we end up building all these different fractions and how we end up feeding our crops, because we're trying to achieve a lot of things, and the better we understand how it all functions, the more intentional we can be about our recommendations. So biodiversity is important, not just in above ground like plants and the different types of things that we're growing, but also the different types of amendments that we may want to apply to the soil. So no one likes to eat the same thing, not even the microbes. So, what we're adding is really going to influence the type of microbes that we add, how quickly things might cycle, how many nutrients we might have available to our crop, what might be just being used by certain type of microbes that will go right to stable carbon. There's a lot of things to consider here. Lots of different sources too. Some are easier to attain than others, which is why we end up often using the same things on our farms. There's crop residues, there's green manures, which are crops grown just for nitrogen value. There's livestock manure and livestock-based compost. And then there's other wastes and other types of compost that farms have access to. And these are all really different. And just look at the color of those, right? All you have to do is look at the color of those, and you know how they're different. Think about all the fractions of organic matter we talked about, and this is no different, right? So you have living, and then you have dead, which would be manure, and then you have very dead, which would be compost, and then you have very, very dead, which would be like biochar, which isn't actually very, very dead. It's burnt. But, but if you're thinking along that same continuum of what we're talking about below ground, when you're thinking about your amendments, think about it the same way, because that's exactly what you're adding. You're adding something that's living, has a lot of nutrients and things that can be eaten up really quick, to something that's dead, which would be like manure. Stuff has already been utilized. It was once living, but now it's kind of broken down a little bit. And then you have composts that have been broken down even more. Okay, they're going to do something totally different than manure or a cover crop residue. And then you have a whole slew of other wastes, but they all fall within that same continuum. All right, so, ultimately, generally, this all comes down to economics and what you have available to you and around you. Sometimes the nutrient content and what you're looking for, but a lot of it has to do with economics and what's the easiest thing for you to obtain, or what you have, most readily available to you. And then, we have to talk about the carbon to nitrogen ratio. And again, just think about this. Think about the color, right? So something that has a lot of nutrients, a lot of nitrogen, tends to be very lush and very green. And if you're somebody that knows anything about forages, let's say, right? When do you get the most protein from your forage? Right? If there's a legume or if it's vegetative. Okay, so it's the same thing when you're thinking about carbon to nitrogen ratios. Okay, when it's green and lush and vegetative, it likely has a low C to N, lots of nitrogen, lower levels of carbon. And then as it turns more brown and sort of more stable, it usually has less nitrogen and more carbon. Now, we need a balance of that. And we need a balance because our microbes need a balance, right? Microbes are 24 to 1. The soil organic matter in the soil should be about 24 to 1. So when we're adding amendments to the soil, if we want them to be broken down, we really want them to be between 30 and 20 for their C to N ratio. Now we want the other things as well, right? We want higher C to N ratios, but they achieve something different. If you want to have cycling of organic matter relatively quickly, right? So that permanganate, that respiration, that water-soluble carbon, and you want it cycling relatively quickly because you need to feed your crops. You don't want to go put out something that's 50 to 1. Okay, so mostly we're trying to add materials that have a lower carbon to nitrogen ratio so that they will be mineralized or broken down by the microbes more quickly, so that our crops and microbes can utilize nutrients themselves. So what is the benefit or downside to adding something that has a higher carbon to nitrogen ratio? Well, it breaks down slower. And why is that? Okay, it breaks down slower because there's more carbon. Well, so what? Well, the microbes again need so much nitrogen and so much carbon. And if there's more carbon than nitrogen, okay, then what they need, they're going to search out nitrogen somewhere else to be able to utilize that material. So where are they going to search it out? If they can't get it from what you just put in the ground, from the soil, like whatever else is there. Okay. So if they take whatever else is there in the soil to break down the straw you just added, what will happen to your crop in the short term? It will be without nitrogen. Okay. It's checks and balances. All right. So eventually, once the microbes actually break down, they find enough nitrogen and they break down that carbon source, nutrients will be released. But remember that continuum? Remember that graph that I showed where it starts with these really fresh residues, and then over time, these microbes break it down, these microbes break it down, and slowly material gets released over time. You're putting slow material in there right from the get-go. Okay, so it takes longer for you and your crops to get anything from it. Now, that doesn't mean the microbes aren't going to work on it. It's just going to be slower, and they're going to take away from your crops in the short term. So that's why often we say, if you're going to put on a sawdust bedded pack material, right? Sawdust, wood, has a lot of carbon. You should probably do that in the fall so that it has time to break down before you plant your next crop. Because you need that time for the microbes to get enough nitrogen to break down the material you just put on the ground. Okay, so it's not bad. It actually is good. You're adding something completely different. You're probably getting a whole new host of microbes, but you're growing crops. So you have to think about that too. So what is your primary objective? Oh, I want it all. Ugh, you people that want it all, right? So then you have to think about it all. Like, how are you going to get the nutrients you need for your crops? That's one type of amendment. Okay. How are you going to maybe build up more longer term, longer lasting carbon? Okay. That might mean adding more compost, like heavily degraded or straw bedded pack, or, sawdust, calf manure, things like that. Okay. They're all great for the soil, but you're going to achieve different things, especially in our time frame. Okay, which our time frame is not 10,000 years or even 100, right? So we have the short term and the long term, and we really need to be working on both while trying to grow the crops that we need to obtain, to sell and make a living on our farms. All right. That must have that's a lot. I think I have more on different types of organic matter. Maybe I'll touch on biochar, and then we can go back and have a discussion around different types of amendments. I know there's been interest in biochar. I watched a webinar on this recently, and it was very fascinating, and I'll share that with everybody. It was like the science behind biochar. It was really great. And but what I did learn was biochar is a scientific term that has gained popularity faster than any other scientific term and has lasted over the longest period of time. It was a very interesting webinar. But okay, so biochar is burnt organic matter. I mean, just to put it, burnt under no or very low oxygen at very high temperatures. And so I just wanted to show these images because it really resonated with me. These are, I think, macadamia nuts or something, or the husks of the macadamia nuts. And then it was put through this pyrolysis process, which is basically high heat with low to no oxygen. And so on the surface, you can see they still look like black macadamia nuts. So it doesn't actually change the structure of the material. And so this is actually considered biochar. And then if you look under an electron microscope, you can see number D here, or letter D, that is after it's been burned. So you can see all the porosity of the material, and then you can see these bigger pores as well in the material. If you look at C, this is the unburned macadamia nuts under an electron microscope as well. So you can see there's a lot of porosity there. But we gain more porosity through pyrolysis, and you get these bigger macropores. And also it changes the chemical structure a bit as well, and you can get a lot of charge. There's, a lot of surface area. You have a lot of different size pores. And this is really becoming all the rage, which is why so many people want to know about it. And it's because biochar has been shown to be able to, do a lot of things once it's added to the soil. And biochar is not new. And I think anybody who's done any studying on biochar knows that, even during ancient times, people were burning materials and adding it back to the soil, and it had these wonderful, properties on the soil, and people still go back to those sites and study them. And so there, the soil science community is continuing to really look at what biochar can do for the soil. And, it's been shown to be able to reduce greenhouse gas emissions. It can really hold on to nitrogen compounds. It can absorb or phosphorus. It can do a lot of things, help with drainage, cation exchange capacity. I don't know, you name it, it feels like it can do it. But it's very, 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 very complicated, even more complicated than everything we talked about today, because depending on the material, the pyrolysis process, the temperature, the the handling of it, like the material itself can be so diverse that it's hard to characterize what exactly biochar as a group can do. And that's what's made this even more complicated, because so many people want to use biochar, but it's hard to really predict what it's going to do because the material itself is so diverse, kind of like composts in a way. So, there are people that are using biochar and swear by it, and definitely, they can't disagree. It's stable carbon. That's what it is, right? And so, but its structure and chemical properties are all really influenced by how it was burned and what it came from. So, it's hard to say, yeah, use biochar, it will do this. And also the quantity that's used is really important. Most of the systems, like ancient systems, they were using biochar regularly over many years to obtain, the benefits that they saw. And now we have studies. I have a study where we're putting on megatons to the acre to try to reduce nitrous oxide emissions. And there is no way that a farmer could afford what we're doing to achieve the outcome. So I think I don't have a lot of recommendations at this point, but it is a material that's out there, that's highly variable, both in, its composition, but also what it can do. And I think, there's a ton of research being done. So time, I think, will bring us more information here. Okay, sorry. I think we should go for questions. I'll put this up too for discussion around different types of amendments and what they will do. This is from a study Fred Magdoff did that shows you water stable aggregates in soil that was amended with manure, grass, straw, compost, and a control. So just again to show different amendments are going to do very different things, and we need to be thinking about diversity of amendments to achieve what we want to achieve with organic matter and soil health.
Thanks, Heather. There's not a question in the chat right now, but if folks do have questions, please do post, or if anybody wants to come off mute, please also feel free. I was wondering if you could speak to the impact on organic matter of practices like subsoiling, and how disturbance cycles can sometimes be useful for some aspects of soil health, but maybe not others.
Yeah. So we are having lots of conversations right now about what we're calling strategic tillage because, we have reality, which is weather patterns that are very erratic, and also keep us out on our fields when we don't want to be there. So we're seeing a lot of compaction, regardless of the health of the soil. Like there's only so much that we can do to protect the soil from compaction when it never stops raining. And at some point, somebody's got to go out there with a piece of equipment, and that's reality. And so for every farm that, has transitioned to no-till or has grass fields and are seeing this severe compaction, there's a concern that we're going to have to use some kind of steel to go out there and open up those soils. And then what do we gain? What do we lose? To be honest, the losses are not well known. Strategic tillage is, it's a new concept, believe it or not, and it's being studied and talked about a lot. But what I do know is compaction will be more detrimental to the overall health of the soil than alleviating the compaction with thoughtful tillage in the very short term. And yes, we will see a loss from doing that, right? If you open up the soil, you allow oxygen to move in. You may bust up some of those aggregates that have protected organic matter. Remember the occluded organic matter? That happens a lot when you till soils, especially when they come out of sod, right? If you've had something in sod for 10 years and then you go in and you till it up, you get a huge boost, you get a huge emissions of CO2, but you also get a lot of nutrients for the following crop. And a lot of that is coming from the protected organic matter that was just opened up. And now it's like food for the microbes. So we will, we'll see some losses. I think it's minor in comparison to the losses we'll see from compaction, not just crop quality and yield, but, the overall physical structure of the soil, and the microbial population and nutrient cycling. So we need to artificially increase, aeration but then go right back to our really good soil management practices.
Thanks, Heather. Sonia, would you like to ask your question?
Sure, it's kind of the flip side of that. I feel like I've also, even as I've heard kind of conversations around selective tillage, I've also heard conversations around like selective compaction, which must admit, doesn't make a lot of sense to me. But the idea that like a small amount of compaction in the top layer can promote biological activity. Can you speak to that, Heather Darby? I'm thinking about like land rollers or people who are advocating for like short-term high intensity grazing.
Yeah, I don't. I know what you're talking about. I think rolling rolling the surface of the soil could be done for a lot of reasons. A lot of the time is to flatten it out so that um, we're making a smoother surface when we need to do some of the various operations that we need to do. Sometimes it really helps with seed to soil contact and the ability for plants to germinate more quickly. And if you're tilling, especially, or even just on the up top 3 inches, and you're making kind of this fluffy seed bed, sometimes when you plant into that, you don't get the best seed to soil contact. So you actually need to roll it to create better contact, which, is advantageous for the seed itself in that moment, but not necessarily like a, soil building strategy, I guess. As far as like high intensity grazing, usually that is done with, it's short but high intensity. So the goal would be not to cause a lot of compaction, but you are going in with a lot of animals and grazing very quickly. I think theoretically the thought is it's so short that the damage is minimal. But yeah, I'm not sure if that's answering your question, but that's
No, I think it aligns with what I kind of thought, which is it didn't make a lot of sense, but yeah, I've heard that a couple of times recently,
yeah.
which maybe it's just like pushing organic matter in to
Yeah,
this
yeah,
surface.
yeah. I mean, I guess, if somebody, a biologically active soil, if you're putting organic matter on the top, it should go back down pretty fast because there should be plenty of biology to do that um, above and below ground. So, yeah, I think it's about seed to soil contact primarily in a fluffed up soil. Strategic tillage as well is now being used because of very high porosity soils that are very biologically active, and the concern of leaching of nutrients through those big pores. We call that macro pore flow. So oftentimes when you start to get all this aggregation and then you get these, seems like they'd be huge, but you get these like channels that could be long and big, and so you're getting leaching of nutrients you may otherwise not. There has been a focus on strategic tillage from that standpoint to be able to break up some of the bigger macro pores. So we're hearing a lot more about that.
Thanks, Heather. We've got a question from Brian. Could you discuss more on the water retention benefit of soil organic matter? Is there enough room for more water storage to mitigate runoff volumes from higher rainfall events? There's examples of 1% additional soil organic matter can hold another 20,000 gallons per acre.
Yeah, so 20,000 gallons is less than an inch of rain, just so people know that, right? Anyway, just putting that into perspective based on how much we see in rain events, right? So I think it does go back to, can we build soils that can withstand 7 inches of rain at one time? Yes, I have seen that. I don't know if it can do that and then do that again the next day, or 7 inches within 2 hours, so you know, our soils, we can build them to be as resistant as possible, but geez, I don't know about some of these events. But the better we do, the more resilient we'll be. And I think, you know, that's really the point here, is that we can't back down, you know, even if it doesn't seem like it's doing much, it's better than what it was when it was less organic matter. And again, you know, Brian, that, you know, is there enough room for more water storage? If we keep, you know, getting 7, 8, 10, 11, 12 inches of rain, we definitely need storage, but we also need infiltration, as, you know, equally as much as storage. Because when we get heavy rain events, we need the water to move through. We need it to be clean as it's going through. And then we need to hold on to water, as I said before, in those smaller pores, so that when we do go through those longer drought periods, there's water for the, you know, for the plants. So holding on to water, yes, you know, I think we can make it through our droughty periods by building organic matter, but you know, intense rainfall, we need those macro pores.
Thanks, Heather. If anyone else has some questions to ask Heather, please speak up. If not, I might ask just a quick, I know you did a lot of work on flooding this year, and just didn't know if you wanted to speak at all to kind of what you were seeing in the fields with flooding impacting anything.
So I one high note was, if I could think of any, was that there was a field that was flooded during Irene, and it was flooded worse this time. But this time, that farm had transitioned to no-till shortly after Irene, and cover crops, and better rotations. And they did not see the damage in that field as far as washouts and soil movement as they did during Irene. And that farm was just so so devastated, but yet so excited about seeing that visual like progress and everything they've implemented, and how it actually really did make that particular field more resilient. So, you know, our practices and the things that people are doing have made a difference for sure. But there are a lot of fields right now that are covered in silt, and people are really asking what to do. There's a lot of compaction out there from last year. And, you know, that's bringing up this whole conversation around subsoiling, and going through, or tilling, disking, you know, and you know, unfortunately, I think we need to be strategic about it, and make sure. And I think this is a role that we can all play if you're working with farmers, helping people figure out how compacted things are, you know, where that compaction is and what they should be doing. And, you know, we all have, well, maybe we don't all have, but we should all have penetrometers. And it's a great tool. And I think we should be going out there this spring and really helping farmers figure out what to do. And I know I've already been called by a few saying, can you come out this spring so we can walk around and see how bad the compaction is? So before we run around tilling, we should do that first.
Wonderful. Thank you very much, Heather.